The Mesoamerican Long Count calendar is a non-repeating, vigesimal and base 18 calendar used by several pre-Columbian Mesoamerican cultures, most notably the Maya. For this reason, it is often known as the Maya Long Count calendar, using a modified vigesimal tally. The Long Count calendar identifies a day by counting the number of days passed since a mythical creation date that corresponds to August 11th. 3114 BCE in the proleptic Gregorian calendar. The Long Count calendar was widely used on monuments. Background: the two most widely used calendars in pre-Columbian Mesoamerica were the 260-day Zocan and the 365-day Hub. The equivalent Aztec calendars are known in Nahuatl as the Tonalpouli and Xiapouli. The combination of the Hub and his Zocan date identifies a day in a combination which does not occur again for 18,980 days, a period known as the calendar round. To identify days over periods longer than this, Mesoamericans used the Long Count calendar. Long Count periods. The Long Count calendar identifies a date by counting the number of days from a starting date that is generally calculated to be August 11th. 3114 BCE in the proleptic Gregorian calendar or September 6th in the Julian calendar. There has been much debate over the precise correlation between the Western calendars and the Long Count calendars. The August 11th date is based on the GMT correlation. The completion of 13 Beactans marks the creation of the world of human beings according to the Maya. On this day, raised-up Sky Lord caused 3 stones to be set by associated gods at lying down sky, first 3-stone place. Because the sky still lay on the primordial sea, it was black. The setting of the 3 stones centered the cosmos, which allowed the sky to be raised, revealing the sun. Rather than using a base 10 scheme, like Western numbering, the Long Count days were tallied in a modified base 20 scheme. Thus 0.0.0.1.5 is equal to 25, and 0.0.0.2.0 is equal to 40. The Long Count is not pure base 20, however, since the second digit from the right rolls over to 0 when it reaches 18. Thus 0.0.1.0.0 does not represent 400 days, but rather only 360 days, and 0.0.17.19 represents 359 days. Note that the name Beactan was invented by modern scholars. The numbered Long Count was no longer in use by the time the Spanish arrived in the Yucatan Peninsula, although unnumbered cachans and tons were still in use. Instead, the Maya were using an abbreviated short count, Mesoamerican numerals. Long Count dates are written with Mesoamerican numerals, as shown on this table. A dot represents 1 while a bar equals 5. The shell glyph was used to represent the zero concept. The Long Count calendar required the use of 0 as a placeholder, and presents one of the earliest uses of the zero concept in history. On Maya monuments, the Long Count syntax is more complex. The date sequence is given once, at the beginning of the inscription, and opens with the so-called ISIG, which reads Zika Hab, patron of Hab, month. Next come the 5 digits of the Long Count, followed by the calendar round and Supplementary Series. The Supplementary Series is optional and contains lunar data, for example, the age of the moon on the day and the calculated length of current lunation. The text then continues with whatever activity occurred on that date. A drawing of a full Maya Long Count inscription is shown below. Earliest Long Counts. The earliest contemporaneous Long Count inscription yet discovered is on Stela II at Chiapa de Corzo, Chiapas, Mexico, showing a date of 36 BCE. Although Stela II from Tacala KBAJ, Guatemala might be earlier. Tacala KBAJ Stela II's highly battered Long Count inscription shows 7 Beactans, followed by cachans with a tentative 6 coefficient. but that could also be 11 or 16, giving the range of possible dates to fall between 236 and 19 BCE. Although Tekala KBAJ Stela 2 remains controversial, this table includes it, as well as 6 other artifacts with the 8 oldest long count inscriptions according to Dartmouth professor Vincent H. Malmstrom. Interpretations of inscriptions on some artifacts differ. Of the 6 sites, 3 are on the western edge of the Maya homeland and 3 are several hundred kilometers further west, leading some researchers to believe that the long count calendar predates the Maya. La Mojara Stela 1, the Tuxtla Statuette, Trezapote Stela C, and Chiapa Stela 2 are all inscribed in an Epi Olmec, not Maya, style. El Baal Stela 2, on the other hand, was created in the Izapan style. The first unequivocally Maya artifact is Stela 29 from Tikal, with the long count date of 292 CE, more than 300 years after Stela 2 from Chiapa de Corzo. More recently, with the discovery in Guatemala of the San Bartolo stone block text, it has been argued that this text celebrates an upcoming time period ending celebration. This time period may have been projected to end sometime between 7.3.0.0.0 and 7.5.0.0.0, 295 and 256 BCE, respectively. Interestingly, besides this being the earliest Maya hieroglyphic text so far uncovered, it would arguably be the earliest glyphic evidence to date of long count notation in Mesoamerica. Correlations between Western calendars and the long count. The Maya and Western calendars are correlated by using a Julian day number of the starting date of the current creation, 13.0.0.0.0, 4 Ador, 8 Kumu. This is referred to as a correlation constant. The generally accepted correlation constant is the modified Thompson-2, Goodman-Martinez-Thompson, or GMT correlation of 584,283 days. Using the GMT correlation, the current creation started on September 6, 3114 BC in the Julian calendar or August 11 in the proleptic Gregorian calendar. The study of correlating the Maya and Western calendar is referred to as the correlation question. The GMT correlation is also called the 11.16 correlation. In Breaking the Maya Code, Michael D. co-writes, "In spite of oceans of ink that have been spilled on the subject, there now is not the slightest chance that these 3 scholars were not right. The evidence for the GMT correlation is historical, astronomical, and archaeological. Historical. Calendar round dates with a corresponding Julian data recorded in Diego de Landa's Relación de las Cosas de Yucatán, the Chronicle of Oxcarts and the Books of Chilambalam. Oxcarts and de Landa record a date that is a ton ending in the short count. Regarding these historical references in the Skywatchers of any rights, all the assembled data are consistent with the equation November 2, 1539 equals 11, 16.0.0.0. Thus for the GMT, or, an alternate term, 11.16 correlation we find that A equals 584,283. The fall of the capital city of the Aztec Empire, Tenochtitlan, occurred on August 13, 1521. A number of different chroniclers wrote that this was a zocan of one snake. Post-conquest scholars such as Sahagun and Duran recorded Tonalpouli dates with a calendar date. Many indigenous communities in the Mexican states of Veracruz, Oaxaca and Chiapas and in Guatemala, principally those speaking the Mayan languages Ixil, Mam, Pocomchi, and Quiche, keep the zocan and in many cases the Hab. These are all consistent with the GMT correlation. Astronomical. Any correct correlation must match the astronomical content of classic inscriptions. The GMT correlation does an excellent job of matching lunar data in the Supplementary Series. For example, an inscription at the Temple of the Sun at Palenque records that on Long Count 9:16.4.10.8 there were 26 days completed in a 30-day lunation. This long count is also the entry date for the eclipse table of the Dresden Codex, which gives eclipse seasons when the moon is near its ascending or descending node and an eclipse is likely to occur. Dates converted using the GMT correlation fall roughly in this eclipse season. The Dresden Codex contains a Venus table which records the heliacal risings of Venus. Using the GMT correlation, these agree closely with modern astronomical calculations. Archaeological. Various items that can be associated with specific long count dates have been isotope dated. In 1959, the University of Pennsylvania carbon-dated samples from 10 wood lintels from Tikal. These were carved with a date equivalent to 741 AD, using the GMT correlation. The average carbon date was 746 plus or minus 34 years. Recently, one of these, lintel 3 from Temple I, was analyzed again using more accurate methods and found to agree closely with the GMT correlation. If the proposed correlation only has to agree with one of these lines of evidence, there could be numerous other possibilities. Astronomers have proposed many correlations, for example, Lounsbury Falls, al. Bowman Stock. Today, the 27th of December 2015, in the long count is 13.0.3.1.1. 2012 in the long count. According to the Popol Vuh, a book compiling details of creation accounts known to the Kaish Maya of the colonial-era highlands, we are living in the fourth world. The Popol Vuh describes the first three creations that the gods failed in making and the creation of the successful fourth world where men were placed. In the Maya long count, the previous creation ended at the start of a 14th Biakton. The previous creation ended on a long count of 12, 19.19.17.19. Another 12, 19.19.17.19 occurred on December 20, 2012, followed by the start of the 14th Biakton's 13.0.0.0.0 on December 21, 2012. There are only two references to the current creation's 13th Biakton in the fragmentary Mayan corpus. Tortuguero Monument 6, part of a ruler's inscription, and the recently discovered La Corona hieroglyphic Stairway 2, Block V. Maya inscriptions occasionally reference future predicted events or commemorations that would occur on dates that lie beyond 2012. Most of these are in the form of distance dates, where some long count date is given, together with a distance number that is to be added to the long count date to arrive at this future date. For example, on the west panel at the Temple of Inscriptions in Palenque, a section of the text projects into the future to the 80th calendar round anniversary of the famous Palenque ruler Kaniche Janab Pakal's accession to the throne. It does this by commencing with Pakal's birth date 9.8.9.13, 08 or 13 Pop and adding to it the distance number 10, 11.10.5.8. This calculation arrives at the 80th calendar round since his accession, a day that also has a CR date of 5 Lam 1 Mol, but which lies over 4,000 years in the future from Pakal's time, the day the 21st of October in the year 4772. The inscription notes that this day would fall 8 days after the completion of the first Picton since the creation or zero date of the long count system, where the Picton is the next highest order above the Biakton in the long count. If the completion date of that Picton's the 13th of October 4772 were to be written out in long count notation, it could be represented as 1.0.0.0.0. The 80th CR anniversary date, 8 days later, would be 1.0.0.0.0.85 Lam 1 Mol. Despite the publicity generated by the 2012 date, Susan Milbrath, curator of Latin American art and archaeology at the Florida Museum of Natural History, stated that, "We have no record or knowledge that the Maya would think the world would come to an end." In 2012, USA Today writes, "For the ancient Maya, it was a huge celebration to make it to the end of a whole cycle," says Sandra Noble, Executive Director of the Foundation for the Advancement of Mesoamerican Studies in Crystal River, Florida. To render December 21, 2012, as a doomsday event or moment of cosmic shifting, she says, is a complete fabrication and a chance for a lot of people to cash in. There will be another cycle, says E. Willis Andrews V., Director of the Tulane University Middle American Research Institute. "We know the Maya thought there was one before this, and that implies they were comfortable with the idea of another one after this, calculating a full long count date." As stated, a full long count date not only includes the 5 digits of the long count, but the 2-character Zocan and the 2-character Hab dates as well. The 5-digit long count can therefore be confirmed with the other 4 characters. Taking as an example a calendar round date of 9/12.2.0.16/14 Yakan. One can check whether this date is correct by the following calculation. It is perhaps easier to find out how many days there are since 4 Aj or 8 Kumu, and show how the date 14 Yakan is derived. Calculating the Zocan date portion, the Zocan date is counted forward from 4 Aj. To calculate the numerical portion of the Zocan date, add 4 to the total number of days given by the date, and then divide total number of days by 13. 13 equals 106,395. This means that 106,395 whole 13-day cycles have been completed, and the numerical portion of the Zocan date is 5. To calculate the day, divide the total number of days in the long count by 20 since there are 20-day names. 1,383,136 20ths equals 69,156. This means 16-day names must be counted from Ador. This gives Kib. Therefore, the Zocan date is. Calculating the Hab date portion, the Hab date Kumu is the 9th day of the 18th month. There are 17 days to the start of the next year. Subtract 17 days from the total, to find how many complete Hab years are contained. 1,383,136 minus 17 equals 1,383,119. Divide by 365 and 1,383,119 365 equals 3,789, and therefore 3,789 complete Hab have passed, and the remainder 134 is the 135th day in the new Hab, since a remainder of 0 would indicate the first day. Find which month the day is in. Dividing the remainder 134 by 20 is 6 complete months, and a remainder of 14, indicating the 15th day. So, the date in the Hab lies in the 7th month, which is Yakan. The 15th day of Yakan is 14, thus the Hab date is 14 Yakan. So the date of the long count date 9/12.2.0.16/14 Yakan is confirmed. Pictunts and higher orders. There are also 4 rarely used higher order periods above the Biaktun: Pictuns, Kalabtun, Conchiltun, and Alautun. All of these words are inventions of Mayanists. Each one consists of 20 of the lesser units. Many inscriptions give the date of the current creation as a large number of 13s preceding 13.0.0.0.04 Ahau 8 Kumu. For example, a late classic monument from Koba, Stela 1. The date of creation is expressed as 13.13.13.13, 13.13.13.13, 13.13.13.13, 13.13.13.13, 13.13.13.13, 0.0.0.0, where the units are 13s in the 19 places larger than the Biaktun. Some authors think that the 13s were symbolic of a completion and don't represent an actual number. Most inscriptions that use these are in the form of distance dates and long reckonings. They give a base date, a distance number that is added or subtracted, and the resulting long count. The first example below is from Scheller. The second is from Stuart Palenque, Temple of the Cross tablet. Scheller 12.19.13.4, 08 Hajor 18 Zek in the prior era 6, 14.0 distance number linking to the era date 13.0.0.0.04 Hajor 8 Kumu Palenque, Temple 19. South Panel G2H6 Stuart 12.10.1.13. 29 Nick 5 Mol 2.8.3.8.01.18.5.3 29 Nick 15 KEH. The tablet of the inscriptions contains this inscription. 9.8.9.13, 08 Ajor 13 Population 10, 11.10.5.81.0.0.0.0.8 The Dresden Codex contains another method for writing distance numbers. These are ring numbers. Specific dates within the Dresden Codex are often given by calculations involving ring numbers. Forstemann identified these, but Wilson later clarified the way in which they operate. Ring numbers are intervals of days between the era base date for Ajor 8 Kumu and an earlier ring base date, where the placeholder for the numeral of days in the interval is circled by an image of a tied red band. Added to this earlier ring base date is another count of days forward, which Thompson refers to as a long round, leading to a final date within the long count that is given as an entry date to be used within a specific table in the codex. Ring number 12, 12.17.3.113 Imix 9 Wo 13.0.0.0.0 Distance number 10, 13.13.3.2 Long count 10, 6.10.6.313 Akarbal 1 Kankan ring. Number 7.2.14.19 Add ring number to the ring number date to reach 13.0.0.0.0 Thompson contains a table of typical long reckonings after setter weight. The serpent numbers in the Dresden Codex pp. 61 to 69 is a table of dates using a base date of 1.18, 1.8.0.16 in the prior era.